For the first section of the back, we're going to use the graph to solve the system if possible, then check our solution, and then label the graph with the type of system. So on the front, we talked about how to find the solution. We need the point or points that satisfy both equations. When I look at this graph, what is that point? How do I know where they're both satisfied? It's where the graphs meet, or where they cross. So what's that point here? That point is +3, +2. So our point is 3, 2. 3 is our x value, 2 is our y value. So this is the point that we think satisfies it. The reason we check our solution is to make sure that we wrote the point correctly, because some of us are still struggling to put the x value in the right place and the y value in the right place. So it's always good to check our solution in the equations to see if we're correct. So let's do that down here. We're going to plug in our x value for x, so that's going to be 3, plus, we're plugging in our y value of 2 for y, so 2 times 2, and we want to see if it equals 7. Well, we have 3 plus 2 times 2 is 4, 3 plus 4 is 7. So is that true, that 7 equals 7? Yes. So 3, 2 satisfies the first equation. Now let's make sure it satisfies the second. We're going to plug in our x and our y value for x and for y. So that'll be 3 times 3 minus 2 times 2 equals 5. Well, 3 times 3 gives me 9. 2 times 2 gives me 4. Does 9 minus 4 equal 5? Yes, it does. 5 equals 5. That is true. So did we write our ordered pair correctly? Yes, we did. Our solution to this system is 3, 2. So our solution is going to be an ordered pair when it is only one solution. Last thing we need to do is label the type of system. So is this one consistent or inconsistent? This is consistent. Remember, on the front of the page we talked about consistent means we have at least one solution. And with inconsistent we have two options. Is it independent or is it dependent? It is independent, because independent means we have exactly one solution. So we have our solution, and then we're going to label it consistent and independent. Let's look at the second one. I want you to pause the video and find the solution, check your answer, and label it, and then check the video to check your answers. All right, let's look at it together. First thing we want to do is find our solution. Well, we just need to look at where do they cross. So they cross at 1, 2, 3, 4, 5, 6, x value of 6, y value -1. So that is our solution, at least we think it is. So let's go ahead and check it to make sure it is our solution. So I'm going to take my x and my y values and plug them in for x and for y. So 2 times 6 plus 5 times -1 equals 7. Well, 2 times 6 gives me 12. 5 times -1 gives me a -5. 12 minus 5 is 7. Does 7 equal 7? Yes. So it does satisfy our first equation. Now let's take x and y and plug it in for x and y in the second equation. So this gives us -1 equals 1/2 times 6 minus 4. Now let's solve it. 1/2 times 6 gives us 3. So I have 3 minus 4, which is -1. Does -1 equal -1? Yes. So this solution, this point, is a solution of the second equation as well. So it does satisfy both. Last thing, we need to label each graph with the type of system. So what type is this? Is it consistent or inconsistent? It is consistent because it has at least one solution. And then this one is independent because it has exactly one solution. So consistent and independent. Last one, look at number 3. To find the solution of this, we need to find where the lines cross. But do these lines ever cross? No, they do not. So on the front of our notes, we looked at what type of solution this has. When I have parallel lines, lines that never cross, this is no solution. There are no points that will ever satisfy both of these equations. So now how do we label it? Is this consistent or is it inconsistent? This one is inconsistent because it has no solution. For this next section, we are going to actually graph them ourselves, then we'll determine the solution, we'll check it, and then we'll label it just like we did above. So for all of these, we're going to put them in slope-intercept form, and then we will graph them and figure out our solutions from there. So first of all, y equals negative x minus 5. We know that this has a slope of negative 1. We know it has an intercept of 0, negative 5. So now we are going to graph it. We go to 0, negative 5. My slope is negative 1, which means I go down 1, right 1, down 1, right 1. But there isn't room for that, so I need to do the opposite, which is up and left, up and left. All right, so here is our first one. Now let's get the second one in slope-intercept. Oops. Well, that one is already in slope-intercept, so we know our slope is 3. Our intercept is 0, negative 1, so let's graph it. We go to 0, negative 1. My slope is 3, so I'm going to go up 1, 2, 3, and over 1. Up 1, 2, 3, and over 1. When we're graphing systems, go ahead and go in both directions until the lines meet. So down 1, 2, 3, over 1. It goes through that point. All right, so here is our system of equations that we graphed. We need our solution. Well, we know that our solution is where the lines meet. They meet right here. So what is that point? That point is x value negative 1, y value negative 4. So we think our solution is negative 1, negative 4, but now we want to check it. It becomes very important that we check it to make sure that we graphed them correctly. Because if we graph them incorrectly and we get the wrong solution, it won't work, and then we can redo it. So let's check it. Here's my x, here's my y. I'm going to plug in my y value for y. So negative 4 equals negative, here's my x value, negative 1 minus 5. Well, minus negative 1 is a positive 1. 1 minus 5 is negative 4, so yes, that works. Let's plug the x and the y into our second equation. So my x is negative 4. We think it equals 3 times negative 1 minus 1. Well, 3 times negative 1 is negative 3. Negative 3 minus 1 is negative 4, so we checked it. You can also check them in your calculator. That is fine. So we found that that ordered pair does satisfy both of these equations. So we are going to circle it or put a square around it because that's our solution. That is the solution that satisfies our system. Now we just need to label it. So is this consistent or inconsistent? This is consistent because it has at least one solution, and then underneath consistent we always have two options. Is it independent or dependent? It is independent because it has exactly one solution. So that's the other part to these problems. Let's look at the next one. Number 5, we need to go ahead and put this in slope-intercept form, and then we will graph them. If you need extra space on these, go ahead and grab an extra sheet of paper if you're feeling squished. So on the first one, to get it into slope-intercept, that means get y by itself. I'm going to subtract the 3x on both sides. So that's going to give me negative y equals negative 3x plus 5. To get that y by itself, I'll divide or multiply everything by negative 1. So y equals 3x minus 5. There's my first one. Then for the second one, to get it into slope-intercept form, I'm going to start by subtracting the 4x. So that gives me negative 2y equals negative 4x plus 6. Now I divide by negative 2. And I will have y equals, well, negative 4 over negative 2 is positive 2. Oops, that should be a negative. And 6 divided by negative 2 is negative 3. So I put these equations into slope-intercept form. There's one, there's the other. Now we graph them. For my first one, I've got an intercept of negative 5. My slope is 3, so I go up 1, 2, 3 over 1, up 1, 2, 3 over 1, up 3 over 1. And then we'll graph the second one. The second one has an intercept of negative 3, so I start at negative 3 with a slope of 2. So I'm going up 1, 2 over 1, up 1, 2 over 1, up 2 over 1, up 2 over 1. Okay, so we graph this one. All right, how do we find our solution? We look at where the lines meet. So where do they meet? Right here. That point is 2, 1. Before we say that's our solution, we need to check it to make sure we did it all correctly. So I'm going to take my x and my y, and I'm going to plug them into the original equation. Plug them into the original to make sure that you did this work correctly as well. So I'm going to take 2 and 1 and plug them in. That's going to be 3 times 2 minus 1 equals 5. Well, 3 times 2 gives me 6. 6 minus 1 is in fact 5. So that's correct. Plug in the next one to the original. 4 times 2 minus 2 times 1. Well, 4 times 2 gives me 8. 2 times 1 is 2. And 8 minus 2 is indeed 6. So that one is correct. So that means that this point is a solution to this system. Now we just need to label. Well, if I have one solution, that means it is consistent and independent. So that is how we will label it. I want you to try the next one. Graph it and then find the solution. Well, if you just tried this one on your own, you may have noticed something kind of different about this. The first one is already in slope-intercept form, so we can graph it. My intercept is -2. My slope is 1, so up 1 over 1, up 1 over 1, etc. Next thing we need to do is get the second one into slope-intercept form. So I'm going to subtract the 4x. That gives me -4y equals -4x plus 8. Divide by -4. And I'll put the equation up here. It gives me y equals x minus 2. What do you notice about this equation? It is the same as this equation. So if I graph it, my intercept of -2, go up 1 over 1, up 1 over 1. They are the same line. So I just graphed a system that has two of the same line. What does that mean my solution is? Well, on the front, we looked at this example where we said if we have just one equation or one line, but we're told it's a system, that means it is an infinite number of solutions because all of those points satisfy both lines. So now that we're on the back, we graphed these equations. They are the same equation. So our answer is infinitely many solutions. And it's really important that at the end we say on the line, and then we tell what the line is. The line is y equals x minus 2. Sorry, it's very squished here, but it's really important that we have this infinitely many solutions on the line x minus 2. If we don't have that sentence, then we're just saying there's an infinite number of solutions and they can be anywhere. But that's not true. Only the points on this line are going to be solutions. So we have to be specific about where those points are going to be. There are that many solutions on this line y equals x minus 2. Okay? Last thing to do is label this because there are infinitely many solutions. This one is consistent and dependent.